Hello everyone, in this video we're going to discuss the kinetic energy related to rotational motion. So if we have an object, let's say like a sphere, and it's rotating around on some axis, and it's not moving linearly, then all of the kinetic energy, the total kinetic energy, is just this rotational energy. And we can think of that as every little particle, every little atom in this ball is rotating, so it has some linear velocity. And when we sum up all of these individual linear velocities, since it's moving around, we can describe the motion for the kinetic energy in terms of this equation. So let's see how we derive this equation. So let's say we have the kinetic energy equals the 1/2 m velocity squared. This is the typical kinetic energy of linear motion. This will be the translational velocity. And we learned previously that the velocity can be related to the angular velocity using r times the angular velocity. Okay, so if we go ahead and we substitute that in, we'll have k equals 1/2 m r omega squared. And so if we distribute that square in, we get 1/2 mr squared omega squared. And you may be noticing that this mr squared right here simply just equals I. So we will get k equals 1/2 the rotational inertia times the angular velocity squared. And that's what we have right here. Okay, so let's look at an example using this equation. So we have Bob spins a 0.1 kilogram top on the table. It rotates 100 times in 25 seconds. The top has a radius of 2 centimeters and can be treated as a solid disk with the rotational inertia 1/2 mr squared. Okay, so what is the kinetic energy of the top? So let's start how we'd always start and list out our variables. So we have the mass, which is 0.1 kilograms. Okay, we have 100 revolutions, and for a time of 25 seconds. We have a radius of 2 centimeters, which we'll want to get that in meters, so that's just 0.02 meters. And then we were told what this rotational inertia, rotational inertia can be described as is 1/2 mr squared. Okay, so if we want to find the kinetic energy, we're going to need the rotational inertia and this angular velocity. And so this is what our rotational inertia is. We have the mass and we have the radius, but we need to get this angular velocity. And so we can figure that out using these variables here. So we want to find this, and this is going to be in radians per second. And so we have that it did 100 revolutions. Okay, and we can create this sort of table with conversion. So we know in 1 revolution, that's 2 pi radians. 2 pi is around a circle. And so that gives us our radians because the revolutions cancel, and so we get 200 pi radians. Okay, and so now we just need to get the angular velocity, which we know is radians per second, and we have the time. So we can simply plug those values in as 200 pi radians in 25 seconds. And so that equals 8 pi radians per second. And so now we have all of the variables that we would need to solve this. So we can go ahead and plug them in. We have our k, which equals 1/2, and then the I is its own 1/2 mr squared times this angular velocity squared. So if we go ahead and plug in our values, we can combine these fractions to get 1/4. The mass, which is 0.1, the radius is 0.02 meters, because we need it in meters, and our angular velocity is 8 pi squared. And so our kinetic energy, if we plug this all in, will be 0.0063 joules. Okay? And so that's how we can find rotational kinetic energy. And so that's kind of the start to looking at energy. In the next video, we'll start talking about work related to rotational motion, how we can relate those. Okay, so leave your questions down below, and thanks for watching.